Hello, my name is Joshua Williams, and this is my Lab 4 video report on oscillations. In this lab, I analyzed the motion of a spring mass system that oscillates in two dimensions, and I'll walk you through the purpose, principles, and computational modeling results and discuss what they mean in terms of energy conservation and oscillation periods. Now, the purpose of this lab was to observe and analyze the spring mass system using Tracker and create a computational model using GlowScript. I compared the predicted motion from the model and observed the motion from Tracker and plotted energy changes, kinetic, gravitational, and spring potential energy to test the energy principle. The main physical idea used in this lab was Newton's second law. It tells us that net force on an object equals its mass times acceleration, or equivalently, the rate of change of momentum. Using this, we can update velocity and position at each time step to simulate the motion of mass using GlowScript. The energy principle states that the change in total energy in a system equals the work done by the surroundings plus any heat transferred. My system includes the spring, the earth, and the block. Because there are no significant external forces, the total energy in the system should remain constant, meaning that the energy is conserved. Here are the key equations that we'll use in the computational model, that being the change in energy in the system, the kinetic energy, and the potential energies. These are the initial conditions I used based on the tracker data and the system characteristics that we got from the lab setup. The initial position and velocity come from the first two data points in Tracker. As you can see, the position and velocity are both relatively at zero. The ball's mass is 0.402 kilograms, and gravity, spring constant, and L naught are all given to us prior. I used the provided GlowScript starter code, modifying it to read my CSV file containing X and Y position data. I updated the force and energy calculations to match the physical setup. The model computed motion step by step using small time intervals to ensure accuracy. Now, here are the results of the computational model. The graph on the left shows the change in energies in the system, delta K, delta U gravity, delta U spring, and delta energy total. As you can see, the delta energy stays at zero relatively throughout the entire experiment. And then on the other side, we can see position versus time of the x-axis and position versus time of the y-axis. And it's not really looking pretty there, and we'll go over why some of those issues may have occurred. Now, some possible sources of error include air resistance, the camera angle, the human error during tracking, all of that. Now, for the what does it mean question, the question asks, for your model system, is the energy principle satisfied? And the answer is yes. The energy principle is satisfied because the change in the total energy is zero. And then it has to make two separate estimates of oscillation periods, and for 5 cycles, both the x and y positions, I compared them and got the x position to be 1.7 seconds and y position to be 1.77 seconds, and the difference is about 0.06 seconds. So, in conclusion, I used Newton's second law and the energy principle to analyze a two-dimensional oscillating spring mass system. My computational model and tracker data showed similar motion, though not really aligning on the exact plots. And the energy plots mainly confirm that conservation was upheld. Overall, the lab demonstrated how physics principles can accurately predict the real-world motion of an object connected to a spring.